about, but probably the most accurate. Instead of assuming the height is always, so if I had like a curve, we were trying to estimate the area under the curve. We've talked about we could do, rectangles starting with the left all the way through there. Pretend all those rectangles are the same width, okay? We have also talked about we could do them with the right hand. So that would be like an overestimate for the first one. The second one would be an underestimate. A midpoint says estimate your height from the midpoint. So the middle of this is right here. So use those rectangles to get there. And I think we can probably see that the midpoint is probably going to be a little bit better. It's not strictly over or strictly under. It will depend on the curve, but it will be a little more accurate than either of those other two options. So that's what the midpoint rule is. This is, your formal definition. I'm not really going to worry about this too much. We're just going to work through it and reason through it. So, this is like the middle four on your homework. I didn't ask for midpoint in all of them. Some I did left, some I did right. But I want to use the summation notation to kind of help me here. So we want the Riemann sum for f of x equals x cubed minus 6x, taking the sample points to be the midpoints, and on the interval 0 to 3 with 6 rectangles. So a lot of stuff there. Yesterday we talked about finding the change in x and the x sub I. So let's start there. Change in x. Ending minus the beginning divided by n, but this time I know my n. It is 6. So we get 3 over 6, or 1/2. The x sub I you can do starts at 0 plus 1/2 I. So we just get 1/2 I. Okay, so two options for how to proceed from here. You can do it like we've done it in the past, and I won't fault you on that if you want to, where you just actually write out all the pieces. So, I don't know, should I do both? I'll show you that, and then I'll show you another way. So, from here, two options. Option one, especially if your n is small like this, you could really just write out the 6 things like we did with over and under estimates. All of these have a width of 1/2. And then you just have to figure out what you're plugging in each time. So you have to think a little bit more. Your first interval starts at 0 and ends at 1/2, or 0.5. If you use the midpoint, what value will you plug in first? 0.25. So it'll be 0.25 cubed minus 6 times 0.25. And then the next one, once you get your first one, you just have to add your change in x every time. So if I add my change in x, which is 0.5, the next one I'd plug in would be 0.75 cubed minus 6 times 0.75. Plus, and can we keep doing this 6 times? Okay. I'm not going to finish writing it out that way, I just want to show you. So if you like that way, you can stick with that. The other option is to use more of our summation notation and the formulas we have for adding things up. So we can do the sum from I equals 1, but I don't need to go up to n. What do I have to go to this time? 6. The width of all of these is 1/2. Then I have to plug my x sub I into my function. So that would be 1/2 I cubed minus 6 times 1/2 I. So in this case, we could use our formulas to add this up. 1/2 cubed is 1/8 times 1/2 would be 1/16I cubed. 6 times 1/2 is 3 times that half would be 3/2 I. So I have 1/16. What is the formula for I cubed? So I cubed is n squared, but my n is 6, so 6 squared, times n plus 1 squared, so 7 squared, over 4. Minus 3/2 times my formula for I is n times n plus 1 over 2. So out of these two options, guys, I don't care which one you use. Whether you want to write out all 6 things and plug them in, or if you want to use our formulas. Okay, what'd you guys get? So 2 options, pick whatever you like. Okay, it doesn't matter a bit to me. If these summation things confuse you, just write out all 6 pieces that you're plugging in and do that. Let's do a few more. We have 2 examples left. I'll do one of them each way. Okay, so I'll do one more probably using the summation ways, and then I'll do the last one using the just write them out and add them up. So you guys can pick what you like. So I want to evaluate the integral from 0 to 3 of x cubed minus 6x. Oh, I guess I put this on here to do it both ways. It's the same problem, isn't it? I didn't even pay attention that I put it on here both ways. So we don't even need to do this. We just did it. I showed you the 2 options already. I just got ahead of myself. Okay, so let's look at this one. Use the midpoint rule with n equals 5 to approximate the integral from 1 to 2 of 1 over x. Okay, so my midpoint, we have to still do the change in x and the x sub I. So my change in x would be 2 minus 1 over what? 5. So my change in x is 1/5, or if you prefer, you can use 0.2 if you like the decimals. My x sub I is my first point, which is 1, plus the change in x times I. So 1 plus 1/5 I. Okay, we're only doing 5 rectangles. So do you think it'd be easier to do the summation with our x's being the 1 plus 1/5 I, or do you think it'd be easier just to find the numbers and plug them in? I think finding the numbers is probably going to be a lot faster here. So let's just do it that way. So all these have a width of 1/5. Okay, the hardest part is figuring out the first number. We start at 1. We add 1/5 or 0.2 to get to the next one. So my next interval starts at 1.2. So if you're doing the midpoint, you plug in the number in between those. So that would be 1.1 is the first thing I plug in. So it would be 1 over 1.1. We have 5 of these. So then if we add our change in x, so if you add 0.2 to that, then it would be 1 over 1.3. 1 over 1.5. 1 over 1.7. 1 over 1.9. So if your n is really big, it's easier to use the summation formulas, but if n is small, it's probably easier just to find the numbers and plug them in. So let's see what we get. Got 0.6919. Okay, is that the true value of the integral from 1 to 2 of 1 over x dx? No, it's an estimate. If I wanted the true value, we could do that. That's what you were doing in the last section of the homework. You would just keep it as 1 over n and do the limit as n goes to infinity. But this is just another way of approximating. Any other questions? So that's really all I have for you. We might move on with the next part at the end of class if we have some time, but I want to give you a little bit of time in class to work on your homework. So, work on homework. I might move on towards the end of class. We'll see how things are going.